Hello there, ATS 114 lab students. Dr. Shragi here, and today we're going to be doing parts of Lab 3 and Lab 4 in your lab manual. The truth of the matter is this lab manual is actually made to work with several different atmospheric science textbooks, and these particular activities don't match very well exactly what we're doing. So in this particular textbook, what we're going to do is we're just going to pull out the parts of two activities that are related to the things that we cover in our course. And so the first part of this is going to be about the radiation laws, which you've already seen. Depending on what section of the course you're in, you may or may not have actually done the math on these basic radiation laws, but you've certainly seen the ideas. For example, one radiation law is Stefan-Boltzmann's law. And this is, in words, you say things like, well, the hotter an object is, the more radiation it's giving off. Okay, well, in the lab, we actually have to do the math. And so we have this very basic equation, E equals sigma t to the fourth. In this case here, E is the actual amount of radiation that the object is emitting, whether that's a square meter of the surface of the sun, or whether that's a square meter of the surface of the earth, or whether that's clouds, or whatever. That's what you're solving for in these problems. And they're going to have an answer. If you plug in the values for sigma and t, and use your calculator, the answer is going to come up in units of watts per square meter. The book seems to have a mistake as to how it got to that point, but the lab manual rather has a mistake as to how it got to that point, but the answer is in watts per square meter. The other radiation law that you have to think about in this lab activity is Wien's law. And again, in words, you probably haven't yet actually plugged numbers into Wien's law, but that's what you're doing today in this little lab. But in words, Wien's law is just that the hotter an object is, the shorter the wavelength of maximum emission. Objects give off radiation at lots of different wavelengths. The question is which wavelength is where the most radiation is being given off, and it's a fairly simple equation there. If you follow the textbook and use the value of c, that constant that it provides you, your answer for this wavelength of maximum emission, lambda max, will be in microns. That's a little mu and then an m. So again, if you just follow the instructions carefully, that's not a terribly difficult problem. Now, a lot of this activity centers around figures like this one that you're seeing in your, on the slide right now. And I actually get really excited about this. A lot of atmospheric science research is this kind of stuff, where there's an instrument that is measuring the radiation at the surface of the Earth. And a lot of the research I do is about, I'm by training an African meteorologist, and I have places where I get data from where there's sensors in various locations around Africa, and we are studying the radiation budget of those places, very much like what you're doing today. It's actually very well tied to active research in atmospheric sciences. So here's an example of the kind of diagram you're going to be using today. This is showing 4 different fluxes of radiation, 4 different flows of radiation that are occurring at the surface of the Earth at a particular station. The curve I have highlighted in red there is shortwave down, or incoming solar radiation. This is radiation that's coming from the sun, making it to the top of the atmosphere, and then making it through the atmosphere past clouds and ozone and all that. This is what actually made it to the ground, shortwave down. And that's in contrast to shortwave up. And you can see here the cycle of shortwave up. Shortwave up is the solar radiation that made it to the surface of the Earth, but then was reflected back up into the atmosphere and back eventually into space. Shortwave up is going to be determined by how reflective the surface is, that is to say, the albedo of the surface. So, like on a snowy day, for example, you may have a lot of shortwave radiation coming down from the sun, reaching the surface of the Earth, but because snow is so reflective, virtually all of that radiation will be reflected back upward. Another term that's shown on here is long wave up, or outgoing long wave radiation. This is radiation that is being emitted by the surface of the Earth, and by Stefan-Boltzmann's law, that would be determined by the temperature of the surface of the Earth. And you can kind of see how there's sort of a little cycle there. At night when it was cooler, there's less long wave radiation being emitted upward, and during the day when the surface is warmer, you are emitting more long wave radiation up. This is radiation being lost. This is heat being lost by the surface of the Earth by emitting long wave radiation. And then there's long wave down. This is long wave radiation, or terrestrial radiation, that's coming from the sky. It's true the sun gives off long wave radiation, but actually not particularly large amounts. Well, it's a large amount of it, it's just that it's so far away. The radiation that we receive from the sky in the form of long wave radiation is almost completely from clouds and greenhouse gases in the Earth's atmosphere. So this is going to be radiation that is coming down from the sky to the surface of the Earth. Again, an instrument at the surface of the Earth could be measuring this. This is heat being gained by the surface of the Earth in the form of long-wave radiation coming down from the sky. Now, in your actual activity, you're working with a total of 6 days of data from a particular station here, but you can now recognize what the format of these diagrams are. They each have 4 curves: long wave up, long wave down, short wave up, and short wave down. And you're going to be making various decisions about, it's going to be talking about things like which day was cloudier or which days were warmer and things like that. Your TA will help you with some of those, because some of them you have to really have noticed things about, like especially the y-axis. How high is the peak in February of shortwave radiation down? How high is the peak in August, etc.? And so do notice the first 3 are about February and the bottom 3 are about August there. The station in mind actually here is Maun, Botswana, and I've decided to show you where that is. I have to admit I'm an African meteorologist and I've never heard of Maun. But I have heard of Botswana, obviously, and so I thought I'd make sure, just so that you know where we're talking about here. Botswana is in the southern hemisphere. It's still fairly tropical. It's roughly at the Tropic of Capricorn. And it is, well south of the equator. That will help you if you keep in mind where we are in the world on these, with this weather station. That'll help you with the answers on some of these questions here. Now, we can kind of make a budget here. Budgets are an important theme in this course. Budgets are an important theme in atmospheric sciences, keeping track of what you gain and what you lose. In this case, we're making kind of a budget of radiation, trying to figure out how much are we gaining from like the sun or from greenhouse gases and clouds in the atmosphere, and how much are we losing in terms of we're reflecting it off the surface or we're emitting from the surface. The net radiation is going to be the balance between the ways in which we are gaining heat by short wave down and long wave down, and ways in which we are losing heat by short wave up and long wave up. And this leads in this lab activity to a diagram that actually depicts the net radiation, the sum of all these terms. And this diagram gets to be a little bit complicated because it has both a y-axis and a second y-axis on the right side of the scale. And let's kind of pick this apart a little bit. One of the curves, which I have highlighted in red, is the net radiation curve, and I've shown you that it has a scale on the y side of on the y-axis on the left side. Now, what's a little bit tricky here, and what as a common mistake that students make, is to not notice that there's a 0 on that axis. Okay, some of these values are positive, and some of these values are negative. It's not the clearest. The people who made the figure could have made this more clear. So there are periods in the day in which we are experiencing negative net radiation. There is net cooling going on. We are losing more heat by long wave radiation up than we are gaining by short wave down and long wave down and so on. Not surprisingly, that's at night. And so at night we are gaining less radiation than we are receiving from the sun and so on. And then during the day there's net warming going on, where we are receiving more shortwave radiation from the sun and I guess long wave radiation from the sky, than we are losing from like long wave up and so on. These are periods when the surface is gaining more heat from the sun and so on than it is losing. And so we would expect the temperature to fall when we are having net cooling. We would expect the temperature to rise when we have net warming. And in fact, you'll see that that is what's happening in the curve that I highlighted in blue, which is the other curve on the diagram. Notice that it is on a temperature scale that is on the second y-axis there. Radiation is not the only factor that is affecting the temperature at the surface of any station here. There are 2 factors that we haven't yet gotten to, like evaporation and sensible heat fluxes and things like that. But for where we are now, we're going to say temperature is being controlled primarily by short wave up, short wave down, long wave up, and long wave down. Now, that kind of gets us through that first lab. Again, we're not doing every question in that lab because not every question is appropriate to our textbook and our curriculum and so on here. But that first part, that came from lab 3, was saying at a particular location, in this case that particular, I think it was an ag research station in Botswana, how were the fluxes of radiation determining or at least influencing the temperature? But now we're going to kind of try to generalize that to a broader, like on a climate scale. At a given latitude, like in general at the equator, or in general at 40 degrees north, the latitude of Omaha and so on, how do the fluxes of radiation influence the temperature? And most of what you're going to be doing in that lab, again, you're only answering a few questions in lab 4, but most of what you're doing in there centers around these 2 diagrams that are on the second page of the lab. And they're a little bit tricky. I want to walk you through the format of these diagrams a little bit. You see how I've highlighted there? Both of these diagrams have the annual cycle as the x-axis. See how it says January, February, March, April, May along there? So this is a graph that is showing how something is changing over the course of a typical year. Okay, now there's two diagrams here. One is for shortwave down and the other one is for temperature. It's a little easier to think about that temperature diagram first. So let's focus on the temperature diagram, which has a y-axis that has temperature in Celsius on it. For that matter, it has a second y-axis that has temperatures in Fahrenheit, but whatever. And I'm going to highlight just one of those curves here. I'm going to highlight the curve on that diagram that is labeled 25 degrees north. What this means is at each place along that curve, you can read off at that time of year what is the average temperature at 25 degrees north. Averaged all the way around the world at 25 degrees north, what is the average temperature? So like in this case, I've went up from August right over to the curve and then right over to the y-axis, and I see that in August at 25 degrees north, the average temperature is 29 Celsius. Okay, so once you understand the format of this diagram, and you can see then there's different latitudes that we can work with. We can see how there's like a different temperature range and so on. Temperature range, let me actually highlight that. Notice that one of the pieces of information you can fairly easily pick off of this diagram is its annual temperature range at each latitude. So for example, see how at 25 degrees north, the range of temperatures here is from about 18 degrees Celsius to about 29 or 30 degrees Celsius, something like that. Okay, that doesn't mean that that's the range of the temperatures at that location, because this is the range of average temperatures. The average temperature in January is about 18 degrees Celsius at 25 degrees north. Okay, that doesn't mean that there aren't places that are warmer or there are places that are colder. It just means the average temperature at that location is 18. And then from that you can also get a sense of what the average range is and so on. Okay. The same sort of thing then can be done with the other diagram. It's just that that diagram, instead of those being graphs of the temperature, those are graphs of the shortwave down. This is the average shortwave being received from the sun, making it through the Earth's atmosphere, past all the clouds, past all the ozone molecules and so on, and making it to the surface of the Earth. And so, well, not all that surprisingly, of course, these two curves are related, right? There's going to be reasons why you're helping in the questions here, you're using this information about the shortwave being received at the surface to start understanding why the temperature ranges are the way they are, why the temperatures change with respect to latitude the way they do, and so on. All right, so there's only about 3 or 4 questions that you're going to do from Lab 4 on this activity. Okay, I hope that this information helps, and your TAs are well prepared to know how to help you with this lab activity if you need any help. And I look forward to talking to you next week. This has been Dr. John Schrage.